Okay. So good morning, good afternoon, and good evening for everyone that's watching this session. So this is the third of, I believe, four planned panel discussions covering different of the programs that are available for you to consider going into second year engineering here at UBC. And again, it's a great chance to learn about the programs that are offered, to learn about the options that are available, and to learn about options that maybe you hadn't given consideration to yet. I think that's one of the strengths of UBC is that we do have so many programs where given a chance to explore and learn, you might find things that really appeal to you in surprising areas and things that you might not have considered. So as part of the AppSci 100 experience, as part of your experience at UBC in first year, we encourage you to learn about these programs, to ask questions, and to give every program a chance to put its best foot forward as well, to see what they have to offer. And so for today's panel, we have three of the programs represented. We have electrical engineering, computer engineering, and engineering physics, and representatives from each of those programs to walk us through what their perspectives are, and a few, I guess, answering questions about where their program fits in with the whole world of engineering and what might appeal for students. So if I could go around and just have a round of introductions for everyone here. We'll go in the order in which I see you on the screen and in which you arrived here on Zoom. So Dr. Tang, if you could introduce yourself to the attendees.
Okay. Hi, I'm Shuo Tan. I'm in the biomedical actually engineering field. I do research in designing optical imaging systems.
Yeah, thank you very much. And next up from engineering physics, this is Jeff Young.
Hello, I'm Professor Jeff Young. I'm in the Physics and Astronomy Department. I'm currently the acting director of the Engineering Physics program. I'm also an ancient alumnus, as is John McKenney, actually.
This is true. Yeah, great to have you aboard, Jeff. And Satish, yourself.
Okay. Hi, everyone. I'm Satish Gopalakrishnan. I'm a professor in electrical and computer engineering with a focus on computer engineering. I also act as the associate head for the undergraduate programs in electrical and computer engineering.
Excellent. Okay, and thank you very much for joining in as well. So today we have a few things enabled. We do have the Q&A queued up, so please feel free to make use of that to ask questions as we go through the session. We will leave most of the posted questions until later on in this format. We've got a few sort of set questions that we will ask and rotate through with the attendees. But also feel free to comment in the chat as well about anything that's sort of relevant to the discussion that's happening here as well. Okay, so as I mentioned, we do have some set questions that were provided ahead of time to the attendees. And again, they're meant to sort of draw out the similarities with programs, the highlights of the programs as well, and things to keep on students' radar as you're considering what programs to go forward with. So I'll again go in the same order that we did introductions, and then I'll rotate things around a little bit. So sure, if you could sort of, as the first question prompt, answer the following. Please describe what your discipline of electrical engineering is about, and maybe some of the main industries where your graduates might work, and the type of jobs that they might do.
Okay. Electrical engineering is actually very broad. It essentially deals with the study and applications of electricity, electronics, and electromagnetism. As I mentioned, it's very broad. It has actually many sub-disciplines. For example, there's the power engineering that deals with generation and distribution of electricity. So that includes transformers, power electronics, generators, motors. Other than that, we also have electronics engineering. So that's what most people are more familiar with, like circuit design, integrated circuits. But we do also have control engineering that's dealing with dynamic systems and the feedback control, such as autonomous vehicle. There's also the signal processing that's dealing with signals and images. telecommunication, so wireless communication. So right now, most people are using internet. That's telecommunication. Instrumentation. Instrumentation can include like biomedical instruments. So there's actually a connection with biomedical engineering. There's also the micro nano technology that's designing very, very small on the nanoscale, microscale electronic devices. So it's very broad, and if you are interested, you can choose any of those kind of subdisciplines. Some of the big companies that our electrical engineers work for include like Boeing, IBM, Google, Apple, GE. Those are some of the international companies. But in BC, there's BC Hydro, TELUS. They all need electrical engineers. Yeah, so as an electrical engineering, your career path can include, you can do electrical controls engineer, electrical design engineer, project engineer, power system engineer, test engineer, or instrumentation engineers. So it's actually a lot of possibility and very diverse area.
That's great to hear. Thank you very much for the overview of the program. So Jeff, the same question to you about engineering physics. So describing what's about, main industries, where the graduates might work, and maybe the types of jobs that they might do.
Right. So briefly, I would say, so explain in the example of electrical engineering, a very large range of subdisciplines within that. Engineering physics is a program that is sort of broad at a slightly different level. And so it's designed to provide a very strong core academic background in everything from math and basic physics all the way through to one or more specific engineering disciplines. And so historically, it was a full year of academic terms more than any of the other programs. But now it's only one academic term more. And the, I think, main philosophy behind the design of the program is to provide students who really do have a genuine interest in the basic underpinning science of engineering as well as the applications to enter the program and spend 5 years developing a wide range of tools and expertise that allows them at the end of the program to go off in many, many different directions. So a lot of people end up going to graduate school, some in mathematics, some in physics, a lot in engineering disciplines, many different engineering disciplines. Electrical, mechanical, geological, biomedical, and in terms of companies, historically, the engineering physics graduates would tend to seek out the R&D arms of large established firms, but also there'd be a large fraction of graduates who seek out or start their own companies and more in a startup sort of mode. And that last entrepreneurial aspect is in the last 10 years been emphasized even more than it had in the past. So a larger fraction than ever are now going directly into startups or doing their own startups.
That's great. Thanks very much for the overview on all the places where EngPhys can take people. Satish, same question for you. If you could describe your discipline, including the main industries where your graduates work, and maybe the types of jobs that they do.
Okay, so computer engineering is very broadly concerned with how we build computing systems, right? And I think this is an important aspect to keep in mind. We think of how to build computing systems across all levels of the system, right? Starting with computer hardware and digital systems, moving up from sort of computer hardware to what we would call system software. So the operating system or compilers and so on, and then going up above that system software level to thinking about application software. So the strength of the computer engineering program is that students get training and exposure to all levels of computing systems. And afterwards, they can choose to specialize in, if based on their interests, whether they want to do more hardware engineering or whether they want to work more in software systems and so forth. And in a way, this is interesting because a lot of the way the computing systems evolve is that you start by prototyping something purely in software, and then you realize I want to improve its behavior, and then you do hardware software co-design, and that's where a lot of the innovation is. It's not purely in software. Most of our graduate students go out to industry. They go to places in Silicon Valley like Google or Apple or Amazon. Now that some of these companies have a presence in Vancouver as well, they are very much, can be in the neighborhood still and be working for lots of these places. Of course, it's not to say that they only go and work at some of these well-known sort of computing places. There's a whole variety of industries where computing is central, right? Whatever it might be, whether it's biomedical engineering. So Cardium, for example, is a company in the Vancouver area, which is a sort of biomedical engineering startup, but tends to have a lot of computing focus. So there are people who verify correctness of software at a biomedical engineering firm like Cardium, and so our computer engineering graduates go there as well. A lot of them eventually do move on to areas like project management, because managing sort of software projects is quite intensive since teams tend to be distributed across the world. And so there is a need for teamwork and collaboration. Many of our undergraduate students also go to graduate school, either in computer science or in computer engineering afterwards. And quite a few of them in the recent years have gone on to startups. They've started their own companies or joined recent startups. I should also mention, which was somewhat of a surprise to me when I came to UBC, is that some number of students actually go on to medical school after doing computer engineering as well. So I know at least a few students each year who go on to medical school, and they sort of see the benefits of understanding how computing can fit in with how we might sort of practice healthcare, or we might actually improve the state of the instrumentation within, say, an operation theater and things like that. So there's a wide variety of things that people can do, and I can tell you more if you have other questions.
Oh, that's great. And as far as some of even the company that you mentioned, places like Cardium, I think that all three programs here are well represented in a place like
Exactly.
that for high tech in Vancouver, and that can really affect lives that way too. And so the next question really touches on that as well. This is about similarity with other disciplines. So when considering your respective programs, what other engineering disciplines do you think your program might share the most in common with, and why? And so we'll spend, this can be a shorter answer, maybe just a minute or so. And we'll start with Dr. Young this time around.
Okay, well, I guess based on the curriculum, there are some core mechanical and electrical engineering courses in the curriculum. So, and probably in terms of where the fraction of students who end up going in the engineering direction go, the majority would be in electrical or mechanical discipline. But certainly many also go in biomedical direction, or as I said earlier, geological. But certainly the biggest overlap is with electrical and mechanical engineering. Yeah, so maybe by way of an example, I mean, Satish talked about the computer engineering program. So an engineering physics student who might be interested in that area I'm supervising a capstone project right now. So those students are looking at quantum computing architectures. And so, you know, they're applying their knowledge of math and physics and quantum mechanics to address a very forefront research topic in computation.
No, that's great to hear about that kind of crossover as well. Satish, about computer engineering and overlaps with other departments.
Sure. So I think, again, when we think of computer engineering, we have to think of the different layers. So you can start with hardware engineering and digital systems, where there is similarities to some aspects of electrical engineering, because the digital systems that we build rely on electrical signals and electronics, and therefore there's an overlap with that aspect as far as electrical engineering goes, right? So if you're thinking about hardware design, there's a clear overlap with electrical engineering. Of course, as Shu mentioned, electrical engineering is quite broad. It's really broad, and therefore the intersection is a small chunk of electrical engineering that overlaps with a piece of computer engineering. When we move up the application stack, for example, so if I think of writing software or thinking about compilers and so on, that's where computer engineering starts having a greater affinity to, say, mathematics, and to even places where we think of computer science to some extent. And in those cases, we think of how do we actually compute? What does it mean to compute? And there, the core knowledge draws heavily on mathematical abstractions, principally. Software itself is sort of unique in a way that it doesn't obey physical laws, and therefore seems somewhat removed from a lot of the other engineering disciplines which are constrained by the laws of physics, right? You can't say, I'm going to violate the laws of gravity because I like it, whereas in a computer, you can always simulate that. Finally, I think that when we move up to the application level, that's where it gets really interesting, because computer engineering then overlaps with just about every field of engineering, because everyone is using computing in their subdiscipline. So if you say, oh, I want to improve the state of buildings today, then you might be involved in sort of computer engineering, but working on sort of instrumentation, sensing, actuation for high performance buildings, for example. So if you think at different layers, it overlaps with some of the different engineering disciplines as well. So I'll try to stop here and handle more later.
No, that's a great way to sort of layer the answer at different levels. That's very good. Dr. Tang, about electrical engineering.
Yeah. So in addition to the other two panelists have mentioned, mechatronics, I would say it's pretty close to electrical engineering, because that's an integration of electrical and mechanical systems. And biomedical engineering is another highly related program in electrical engineering and biomedical engineering. So there's actually the specialization in dealing with biomedical instrumentation and then the biomedical signals and images. So that's kind of a highly related area as well.
Yeah, thank you very much. And the department, electrical and computer engineering, is well represented for sort of those health related fields and the impact that can happen in there too. And actually that goes to the next question. Didn't even realize about research areas in your respective programs and departments. So what are a few examples of research areas in your discipline? And so just a few, maybe a minute about that. So we'll start with Dr. Gopalakrishnan.
All right. So again, I think I will use the same sort of layering approach. If I were a hardware designer, I'm really keen on things like, ultimately people are running software, they're running applications on top of the hardware. But I want to say, how can I make this more energy efficient? Because a lot of the computation we perform today may be running off a mobile phone or even on my watch. And so I don't want to keep recharging my battery. So as a computer architect or hardware engineer, I'm really interested in how can I perform this computation with as little energy as possible. And so there's this crossover between computer engineering and circuit design where we say, can I improve this performance? For example, if I want to improve how Siri recognizes voices and performs certain commands, how do I do this on my watch itself instead of shipping off the data to some data center somewhere else for privacy reasons and whatnot? So there's a lot of work that happens at that level. If we move up to the operating system and so on, we're thinking, computers today are distributed across the world. There's a lot of computation that needs to be coordinated. How do I make this more efficient? How do I make this more correct? Because when we are building systems with these days, millions of parts, millions of computers somehow working together, there are bound to be bugs or mistakes. And so we want to be able to detect mistakes or be able to deal with faults and continue working. So there's a broad emphasis on high performance and highly reliable systems at that level. At the application level, we get interested in often, because programmer productivity is influenced by how quickly we can generate correct programs, how can I provide tools or other techniques to make sure that programmers can very quickly arrive at correct implementations? A huge productivity loss comes from bugs in software or security vulnerabilities and so forth. So there's a huge effort to say, how do I know that a piece of software is correct? How do I know there are no security vulnerabilities? And again, if we think of where we are heading with, say, autonomous vehicles and so on, those are clearly pressing challenges, because how do I know that my machine learning software that's running on my car is actually doing the right thing? And even if it's doing the right thing, how do I know that someone can't attack it, because someone can't hack my car and make it do other things? So those are all sort of critical research questions of the day.
Yeah, thank you for that again. And again, the layers of and levels that you can approach these problems are really interesting. So Shuo, about electrical engineering and all the sort of hot research areas in that field.
Yeah, I want to give an example on Internet of Things. Now, many things are being built with Wi-Fi connection. That means they can be connected to the internet and to each other. And that's the name of Internet of Things. It is actually the future. It has already enabled many devices, home appliances, cars, your surveillance camera, your garage door. Those have already been connected on the internet, and they can exchange data of the internet. So that has been kind of a very, very promising future. Another example is quantum computing. For example, there's a quantum hardware, programmable quantum devices. That's another very active research area in this discipline.
No, those are great examples. Yeah, thank you very much for that walkthrough. And Jeff, the same question about engineering physics and areas of research in that discipline.
Yeah, sure. So in 1 minute, I'll just focus on one sort of sub area. I mean, a lot of research is focused on trying to develop new materials and new instrumentation that could, completely replace existing integrated circuit technology. And most of that research involves operating at the atomic scale, manipulating individual atoms or individual molecules. And so this means conceptualizing circuits and figuring out how to control the placement of individual impurity atoms in silicon chips and connect them with individual photons or particles of light. And then on the molecular scale, being able to manipulate individual DNA strands and be able to characterize them in a very efficient, high throughput manner. So.
Oh, those are great challenges to have, and tools in the ENPH discipline that can get people there as well. I'm going to switch gears a little bit and think about the student experience as you go through and some of the program features. So with that in mind, what would you say are some of the key features about the way your program is structured at UBC? And that includes maybe opportunities for students in gaining experience or in tailoring their degrees. So key features of the program, opportunities for students, and tailoring their degree. Shuo, if you could comment about electricals approach.
Sure, yeah. So since electrical engineering is very broad, some students might wonder, is it very difficult to study because I don't know what to focus on? So the program is very structured. So in year 2 and year 3, you're going to take a series of well-designed courses that will help you to build a solid foundation in electrical engineering. For example, circuits, signals and systems, electromagnetism, control system, computer programming, which is also a tool that we use. With that foundation, then in your 4th year, you can then move on to choose your concentration of area, your specialization. So you can choose some different courses in the specific area that you're interested in power systems or nano microsystems. So you can take those as advanced elective courses. So with your foundation and then with your specialization in 4th year, then you basically can choose any specialization area you want. One of those area is the biomedical engineering option. So it has the specific electrical engineering flavor, but it deals with biomedical instrumentation or signals. Another thing I want to mention is about our design courses. We do have design studios in year 2 and year 3. And that will give you hands-on experiences and teamwork experience. And then the capstone project in year 4, those are industry proposal projects. And that will give you kind of a very good experience, again, to really solve an industry proposed project. So that will give you very well-rounded experiences and teamwork opportunities.
No, thank you very much for the walkthrough and all the opportunities right from 2nd year all the way through as well. So Jeff, about engineering physics, so key features of the program, opportunities for students, and maybe tailoring their degrees.
Yeah, so the core engineering physics program includes math and physics in every year up until 4th year. Advanced courses in both math and physics. It includes core mechanical and electrical engineering courses up to the 3rd year level. And it integrates hands-on lab and project experience starting immediately in year 2, even though you don't necessarily have all the theoretical background to understand exactly what you're doing. You get exposure starting from year 2 and in each year culminating in 2 capstone projects in 4th and 5th year. There used to be various specific specializations in different engineering fields that you could choose optional courses within. But recently that's been done away with, and so the program is completely accredited while still offering a huge flexibility in your technical elective courses. So a number of people now use their technical elective courses to take business and entrepreneurship courses, for instance, not necessarily engineering discipline related courses. Others take astrophysics or particle physics, and others take core advanced engineering option courses in electrical and mechanical.
Well, that's great to know that there's that range that people are interested in, and maybe even in the same students going through the program to to take a little bit of all those different areas. Satish, for computer engineering, so key features of the program, opportunities students have to gain experience, and maybe tailor their degree as well.
Right. So I think at the sort of broad structural level, computer engineering and electrical engineering share a lot of commonalities because they're both programs that the Department of Electrical and Computer Engineering offers. And so, again, there are project experiences in the second year and in the third year, and currently sort of a 2-term capstone project. So there is a lot of opportunity for this sort of hands-on work that some students seem to enjoy. We've also tried to accommodate cases where students are interested in foundations over sort of, I want to do this hands-on stuff, which is perfectly fine because sometimes, 3 terms of hands-on work is more than sufficient. You don't necessarily need to do 4 terms of sort of project work, but we do sort of try and accommodate that. There is a lot of, the second year lays the foundation for the sort of breadth that involves both digital systems, circuit design, and software systems. And from there are opportunities for computer engineers to focus more on software and networks, or they can choose electives that lead more towards hardware and digital systems. The other, I think one of the key feature, which is also shared by electrical engineering, is that these are the only 2 engineering programs that have about 6 credits of completely free electives where we encourage you to take courses across campus. Again, lots of students do end up taking courses that are related to their discipline, but it's not required, right? We would, the common joke is, well, can I take underwater basket weaving? And if UBC were to offer the course, you should try to take such a course because it seems totally cool that you can weave baskets underwater. However, you have the opportunity to explore, right? And so there is freedom, and there are opportunities to take electives in computer science, in mathematics, in statistics. Again, all of these are disciplines that are closely related to computing and the tools you need to build better computational systems. And again, we see students taking electives in, say, math and statistics apart from computer science, of course.
Oh, thank you very much for the sort of the description of all the flexibility that happens. Underwater basket weaving. Oh, I'll keep that on my radar as well. So keeping sort of an eye on the sort of the student side of things, could you comment on the student experience in your program? So what is the student experience going through your respective programs? What might that be like? So I believe it will be back to engineering physics. If Jeff could comment on that.
Yeah, so the engineering undergraduate activity or club in engineering physics is extremely active. They, non-COVID times, have a very nice dedicated club room. They're heavily involved in, for instance, managing and running a mentorship program for students immediately when they enter in second year. And they are very active in both clubs and ELEC, and I think you'll find it an extremely welcoming group of students. And many people, upon graduating, basically say that they feel that they got as much or more out of their interactions with their peers than they did from the technical content of that program. So.
All right, thank you very much for that insight. And Satish, about computer engineering and the student experience going through.
So I think, again, the student experience is very much driven by a lot of the sort of enthusiastic peers that you have. And so from that perspective, lots of students are involved with student teams again, because there is, of course, a computing component to many teams, for example, UBC Rocket, or the sort of solar car project and so on. There are clearly sort of aspects that are computing related. So I think that that's a really important aspect, because you sort of work with students from other disciplines or other domains. And as an individual, you really begin to appreciate other domains. I think this is sort of really important, because computer engineering by itself is a very domain agnostic field, right? We're not focusing on the application domain. We're saying, I'm here to build computing systems. What do you use it for? And in fact, I think as the world evolves, it's important for computer engineers to actually gain some amount of domain expertise, rather than saying I'm a generic sort of software engineer or a generic computer engineer. We are moving towards more sort of, say, computational biology, for example, and it helps to know some of these things. So working with, say, the biomedical engineering student team or UBC Rocket, or I just picked these two as examples because I know people there, and you can really build up on those skills. The other aspect, of course, I mean, somewhat shamelessly, I will admit that if there are good ideas, we steal them. And so we've sort of stolen the idea of the mentorship program from engineering physics. And so we now have a sort of mentorship program for second-year students in electrical and computer engineering as well, which is sort of important because it's a largish cohort. We have about 300 students across electrical and computer engineering. And so scaling some of the student activities is something that we're investing a lot of energy into.
No, thank you very much for that overview of what students are sort of getting prepared for. And Shul, about electrical engineering and the student experience going through.
Yeah, I want to talk a little bit more about the extracurriculum teams. So in those kind of extracurriculum teams, you get to interact with many other disciplines. For example, like computer programming and software and mechanical engineering. So for example, in UBC Solar, they are building a solar powered car. So the renewable energy and the battery, of course, electronics, that's the electrical engineering part. But then you also get to work with computer engineers in the same team. Another example is the UBC Thunderbolt Club. They build autonomous soccer playing robots. They attend competitions annually. And in this design team, you also need to learn about sensors and also feedback control. And of course, there's also the mechanical part and the computer engineering and software part. So you get to interact with all the people from different disciplines. You really get to do teamwork, and also you do the interdisciplinary kind of activities together. Yeah, so lots of opportunities.
That's great, and knowing that so many of the students in electrical will participate in this way across those teams that you mentioned, and across really a broad spectrum of different teams as well. Okay, we have one more sort of formal question to go through, and then after that we can answer any of the questions that might appear in the Q&A. So if you have something that's in your mind about the programs, anything in particular about one program, or about to ask all the panelists, go right ahead and post there, and we'll get to it in just a bit. But the final question I've got is a complete the sentence question for all of you, and that is, complete this sentence. You should consider joining this discipline if, and we'll leave it to you to answer. So, Satish, I think we'll start with you. You should consider joining computer engineering if.
You should consider joining computer engineering if you clearly want to make a difference to how we view and interact with the world, as well as if you're really committed to sort of learning new things, because the world is changing at quite a rapid pace, and software in particular changes very quickly. So if you love the challenge of learning new things really quickly, then computer engineering is for you.
Excellent. Thank you very much. And Shul, about electrical engineering. So you should consider joining electrical if.
Okay, so as Satish mentioned, we are living in a rapidly changing world, and everybody has a smartphone, and we are talking about buying an electrical car, and all of those are related to developing new electronic systems and gadgets. And if you are interested in and passionate about innovation, technology, then you should consider joining electrical engineering.
All right, thank you very much. And Jeff, to you about engineering physics. You should consider joining engineering physics if. Oh, still on mute. Still on mute. I could tell it was a good response.
If you're passionate about math, physics, and applications, if you love a challenge, and if you want to spend 5 years developing a skill set that'll serve you well in anything you do in the future.
Excellent summary of the programs there. So thank you for going through and answering these formal questions. I don't see anything in the Q&A right now, but there are a couple of things that I had in mind as I was listening and thinking about questions that that come up for students, because I as part of the first year teaching team, they'll often hit myself up and other of the instructors about programs. So here's a question again for all of you about maybe common misconceptions that people might have about your program. So when you talk to students and you get a sense of where they're at, or even with students that have applied to your programs, what's a misconception that they may have that you think would be appropriate to address, if there are any? Maybe I'll throw that open to everybody, because I don't know if you've prepared anything, but I see.
Okay, so maybe I'll take a stab first, because there's a stereotype that computer engineers or software engineers spend all their time in a cubicle staring at a screen and writing code, which is actually quite far from the truth, because a lot of the work in building computing systems is brainstorming and not really, the actual amount of time you spend writing code sort of tends to diminish. You're really doing a lot of design. You're interacting with clients. These might be internal to your organization or company, or external, but there's a lot of client interaction, because in the engineering process, a big chunk of time is actually figuring out what it is that you have to build, right? It's actually the biggest challenge is figuring out what is the right thing to build. And the same is true for computing systems or software systems. And so there's a lot of client interaction, working with people or experts in other disciplines. And therefore, it's not that you spend all your time just staring at a screen and writing code. In fact, there have been studies over the years that ask, figure out, how many lines of code does an average software developer write in a day? And that's about, 10 to 12 lines of code in a day, right? There's a lot of other work to get that code right, but you're not writing a lot of code, because much of it is figuring out what you should be doing. And that's one thing that I want to sort of change, because it's a myth, and you do get a huge amount of opportunity to interact with a variety of interesting people. These days, data journalism is one thing that's pretty cool. And so you work with journalists on how to actually collect data, how do you present data, and how do I process data really quickly? With elections coming up in the US, you might say, well, how do I process data really quickly, visualize it, things like this. So these are all really interactive and a lot of fun. And therefore, one should view computing in that light.
Okay, no, that's good. Are there any other sort of misconceptions to address between electrical?
I can say a few words. I wouldn't say it's a misconception. I think there's quite some confusion about what's the difference between electrical engineering and computer engineering, because we're in the same department. I would say computer engineering deals with computers and computing systems. Electrical engineering is actually covering a lot of those other disciplines like communications, signals, controls, and power systems. So there's quite a lot of difference between those two programs. And also students ask, can I still take computer courses if I'm enrolled in electrical engineering? Yes, you still have a lot of opportunities in taking computer courses. There are actually several courses already built into our second and third year curriculum. And then in the fourth year, there's the free electives and advanced electives. That's where you can also take more computer courses if you really want to kind of merge those two disciplines.
So I do, maybe I'll use the opportunity to answer one other question that's fairly common, which is, what is the difference between computer engineering and computer science? and so on. So I think it's important to note that computer engineering is about understanding the entire scope of a computing system, including the digital, or as we are moving towards other forms of devices, so analog or quantum devices. How do I think of computing with all sorts of devices? But also I'm focused on thinking about software and so forth, right? So computer engineering provides that full spectrum view of a computing system, whereas often, and in particular, this is true at UBC, the computer science program tends to treat a lot of the hardware modules as black boxes and focuses on, say, software and algorithms. So that's important. There's another question that's been posed about software engineering. So right now, computer engineering does not have a software engineering option. We eliminated it simply to allow students a lot more flexibility, and very few sort of computer science students also opt for the software engineering option within computer science. The real answer is, if you want to do work in software, your actual degree or qualifications are not all that significant. Your employer is interested in what you can do and not what kind of degree or what your transcript says. And so it's more important to have true skills rather than proxy skills.
Yeah, no, very good. So check that off as well. So thank you for that. There's a couple of questions about sort of the number of students accepted into each program. And I was just looking up what the numbers were for this past September. And it basically comes in multiples of 60. So engineering physics had just about 60 students. Computer engineering had 120. And electrical engineering had 180. That were accepted into the programs. And this upcoming year, the proportions should be roughly the same coming up. We've got slightly more first-year students, so every program might grow just a little bit, but something along those lines as well. So there's a question about already having coding experience when enrolling in CPEN. So maybe this is good for background experience in any of the programs as you're going forward. So coding in CPEN, or maybe other experiences that you might be expecting for your students coming out of first year, going into second year in your programs.
Right. Maybe since the question for now asks about
coding, yep.
Experience, I would say it definitely helps. There is a rather quick ramp up that happens in second year, and the more experience you actually gain, the better prepared you are for second year. So I would say that one should really use what you've learned in a course like Applied Science 160, and then try to extend that knowledge over the summer between first and second year to really be able to sort of engage with the computer engineering program and get the most out of it. If you don't have a little bit of that preparation, people do fine, but you miss out on some of the benefits that come from having some prior engagement, which really makes you appreciate the second year material a lot more, right? So I think that kind of background, just how do I think computationally, is really, really helpful. And I would say it's not true just for computer engineering. In general, the ability to use computation is valuable across all the engineering programs these days.
Yeah, I was just gonna, if you hadn't said that, I was gonna say that. So yeah, I think that advice applies to every engineering program.
Mm.
Yeah, I want to add a little bit on this. I think with this general first year curriculum, you've taken several math courses and physics courses, and those can very well prepare you for electrical engineering, because those are kind of the most important foundations for learning in this field.
Oh, very good. So thank you for the insights and overviews of your program. I think at this point, we're just about kind of at the end of time for this session. And by no means is that the last time you get a chance to learn about these programs. There's multiple opportunities to get a chance to see what programs are like up close. The most immediate one happens to be the Engineering Open House, which is this Saturday, November 7th. So there are events scheduled throughout the day, you can check online, follow the link that we provided in the AppSci 100 session, or just look up Open House Engineering, UBC, and you'll be able to see information. Every department will be there represented, and having students and faculty sharing their perspectives. So it'll be these 3 programs represented today, and all, I lose track, 14, 15 programs we have available in second year. We got a lot. And getting a chance to learn and to share with them. And also throughout the year, there will be other chances to learn about computer engineering, electrical engineering, and engineering physics through department events as well. And so with that, I'd like to take a chance to thank the panelists for taking time out of your schedules to come and share your perspectives on your programs. Very much appreciate it. It's a different kind of format. I'm happy that we were able to share and get some overlap between the different programs and to hear some similar stories and similar companies and experiences, and also the things that distinguish you from one another as well. So Satish, Shuo, Jeff, thank you very much for your time. Very much appreciated.
Thanks for moderating, John.
Yeah.
Thank you, John.
Yeah, and with that, I will stop the record, and then we can all relax. But thank you very much, and good luck to the students for learning more about all these programs. And where is that record button? I keep looking for it.